Okay, everybody. So last time we talked about temperature and pressure and the ideal gas law. This time we're going to move into heat transfer, which is not only just the state of a particular material, but how that material changes its temperature over time. Okay, so the place we're going to start is with the idea of thermal equilibrium um, and how you achieve thermal equilibrium. So let's say I started with a situation where I had one block of material here that was hotter than the block of material down here. Um, the molecules up here, let's say this is a solid, would be jostling more uh, vigorously, right? We know that their kinetic energy would be higher. The kinetic energy of these molecules would be lower. Well, what would happen is that the faster jostling up here would create collisions with the molecules on the bottom. And when you have a high energy molecule colliding with a low energy molecule, the tendency is for the energy, that kinetic energy, to be transferred from the high energy molecule to the low energy molecule, right? If I have something standing still and I throw a baseball at it, like let's say a milk bottle standing still, and I throw a baseball at it and it hits the milk bottle, um, in general, the baseball is going to lose some momentum and the milk bottle is going to gain some momentum. That's not that hard to understand. Uh, when that happens millions and millions of times here, you get a transfer of momentum and kinetic energy from the high energy material to the low energy material. And it keeps happening uh, basically until they have the same amount of energy, right? Because if you just let them sit there forever, then eventually all that kinetic energy is going to move equally into this lower material, and you'll have what's called thermal equilibrium. That is, they'll both be at the same temperature. This idea leads to the zeroth, zeroth, that's even hard to say, so the zeroth law of thermodynamics, which basically says that temperatures are going to be the same um, no matter where you're measuring them. Okay, so technically what it states is that if one object is in thermal equilibrium with the second, and the second is in thermal equilibrium with the third, then the first is in equilibrium with the third. I should say third. In terms of temperature, this just means it's sort of the transitive property for heat. If temperature of A is equal to the temperature of B, temperature of B is equal to C, then A is going to be equal to C. It's just saying that temperature is a measurable and consistent um, indicator of the kinetic energy of a material. So what does that have to do with heat transfer? Well, that transfer of thermal energy from one material to another is really crucial. It's a sort of central process of heat transfer, the spontaneous transfer of energy due to temperature difference, right? Because two materials have different kinetic energies and are colliding with each other, eventually you're going to move some of that energy from one material to the other. We measure heat as a form of energy, so its units are in joules. Sometimes you'll see calories or kilocalories used. When you look at a food material and it tells you how many calories you have, that's essentially a measure of heat energy, right? How much energy is in that food that your body's going to be able to withdraw from that food. The interesting thing there is that when it says calories on your food box, that actually means kilocalories. So don't if you start doing some equations with the calories that you look on a box, those are actually kilocalories, 1,000 calories. So then we ask, well, how much energy how is required to change the temperature of a material? In other words, how are temperature and heat connected to each other? And we need something called the specific heat of a material to know the answer to that. So we have a governing equation that is stated Q equals mc delta T. Q is the heat transfer, how much energy is being moved into an object. M is your mass, C is your specific heat, and delta T is your temperature, right? So any material is going to have a specific heat, and basically it tells you how much energy is required to change its temperature. So let's do a quick example to see how that works. So units for specific heat are joules over kilograms Kelvin. That is that amount of energy needed to change a certain mass a certain number of degrees. So let's say we have water. We want to know how much energy is needed to raise the temperature of a quarter liter of water from 20 degrees Celsius to 80 degrees Celsius. We would need to know basically our mass, right? And we need to know our specific heat. So to find our mass, we need to know our density, okay, because what we're given here is a volume. And we would look up both of those things in a table, right? So you in your textbook or on the internet. So the row of water roughly is 1 kilogram per liter. And the specific heat of water is 4186 joules per kilograms Kelvin. So we want to know Q, we want to know the heat transfer, right? So we have 20 quarter liter. We want to convert that to kilograms, so we're multiplying it by its density, which is kilograms per liter, right? So our liters are going to cancel out. We multiply it by our specific heat and by the amount of temperature change. And this tells us that we need 62.8 kilojoules of energy in order to make that temperature change for that volume of water. So that's one way of thinking about how energy changes a material. But sometimes we can add energy to a material and the temperature stays the same. And that is during a phase change. Okay. So why does this happen? Well, we know that when we add, when the temperature raises, the kinetic energy of our molecules is increasing, right? Well, what happens when you're adding energy during a phase change is you're really adding energy just to break the bonds between two molecules. It doesn't change the kinetic energy of the molecules. It just moves the molecules further away from other molecules and weakens those bonds. Okay. So we can take the example of evaporation and its cooling process, right? So you sweat in the summertime. Why is that cooling your skin? Well, in order to turn that water into a vapor, you need to add energy to break the bonds between those liquid molecules. And so even though the water, when it turns into vapor, hasn't changed temperature, right? It still requires energy, and that energy is coming from the skin. And so here we have before we talked about adding energy to change temperature. Here we're adding energy to change phase. So you can actually look at a plot of temperature change versus heat transfer. And we can see how much energy is required to make particular changes. And this is pretty interesting in the sense that the amount of energy to move water from 0 degrees to 100 degrees, in other words, from barely unfrozen to just about boiling, is what? Maybe about 100 calories per gram. That's our units down here. To change it from water to steam is a huge amount, right? It's like about 5 times as much energy to change that from water to steam than it is to raise that temperature by that much. So you can see that phase change requires a lot of energy. And we can calculate that energy by using our coefficients of latent heat. Okay, so this is our latent heat values. And again, we'd look these up in a table. So this is the latent heat of freezing. So that's what's required to make this change from ice to water. And this is the latent heat of vaporization, which is the change required to go from here to here. Now, at higher temperatures and pressures, phase change can get more complex. And we can see that when we look at what's called a pressure temperature plot, or sometimes also called a phase diagram. And we can see the relationship between phase, pressure, and temperature in this plot. So if we look at this, notice these values over here, right? 218 atmospheres is a very high pressure. 1 atmosphere is just the pressure of environmental pressure. And then this pressure is really low, okay? So near vacuum pressure. So in the normal pressure realm in here, as we lower the pressure of, or lower the temperature, right down here, we go from 374 Celsius, which is very high. We get to 100 degrees, right? And our vapor turns into liquid. That's what we would expect. This is what we're used to. And then we would cool it further and further. And then at 0 degrees, it turns into a solid. This is the world we live in, this line right here. But in the worlds of high pressure and low pressure, you get different behavior. And in fact, one of those interesting behaviors is that at a certain point, called the triple point, you can have liquid, vapor, and solid coexisting. In the same way that when we're boiling water, we have vapor and liquid coexisting, right? Or when we have a glass of ice water, we have both ice and water at the same temperature. At this triple point, which is at a very low pressure point, we can actually have all three existing. And this is a useful point for physicists and others, because it only exists at one place, right? So if you know you have all three of those at the same place, then you know what your pressure is and you know what your temperature is. So that's a phase diagram. Finally, one last point is that vaporization can happen below a boiling point, right? We know that because we see sweat evaporating from our skin. So how does that work? Well, we know that molecules have a random motion. We know that the kinetic energy has to do with temperature. But we know, too, that the randomness of that energy means that if I have water at, say, I don't know, 30 degrees Celsius, a hot day, the average kinetic energy is going to be at that 30-degree level. But there are going to be some of those molecules that are moving much slower than that, and there are going to be some molecules that are moving much faster than that. Okay, so those really high energy molecules are actually going to have enough kinetic energy that they can break intermolecular bonds. So you actually have evaporation, or in some ways kind of boiling. We don't call it boiling. You have some molecules able to break out of that liquid phase into the gas phase. So that's how you can have sweat evaporate at temperatures under 100 degrees C. But it also does something interesting, because you're taking away a really high energy molecule, right? Of the spectrum of kinetic energy in those molecules in that material, you're taking away the ones that have the most energy. What that does is it lowers the temperature of the remaining fluid, okay? Because you've taken a lot of kinetic energy away. It lowers the average kinetic energy of the remaining molecules, and that means the temperature is lower. And then your skin has to use energy to warm that now cooled fluid back up to the temperature of the skin. And that's how evaporative cooling works. This is actually super cool. And if you want to talk to me more about it, I'll talk your ear off, because I think it's really interesting. So that's all we're going to do for today. And we'll catch you next time.